we've been talking about radioactive decay. We want to quickly talk about the nuclear bombardment reactions. So when we say we now have these nuclear bombardment reactions, remember what we simply have is the nucleus or a nuclear particle heating at the nucleus of something, and it's going to change. So that is what we have. An example is this transmutation, where by transmutation we said we'll be having the nucleus of one guy being bombarded by the nucleus of another element, or by nuclear particles of another element. They will heat it and it's going to change. When this nucleus is hit by another nucleus or by nuclear particles like an alpha particle or a beta particle, then it's going to change into a different nucleus. And that is transmutation. It's a type of a nuclear bombardment. What is special about nuclear bombardment reactions is this. Radioactive reactions are spontaneous. That is a key thing about radioactive reactions. Don't ever forget, they are spontaneous. They happen on their own. You cannot make them happen or stop them from happening. But now these transmutation reactions, there is a hand of man in it. We can affect them in the lab. We can play with them in the lab. We can make them happen. We can make them happen faster. All these things in the lab, right? That is something that we have, that what we were not getting from radioactive reactions. They were spontaneous. They were happening on their own. We couldn't do anything to change it. But now we have our hand. Here's an example of a transmutation reaction. This was an important one. So you see, these transmutation reactions were actually helpful to us because they helped us get protons, they helped us get neutrons discovered. They helped us discover these things, right? Now, what Ernest Rutherford did is, I'm sure some of you might remember what the Ernest Rutherford experiment, where he fired alpha particles, and he was able to tell us that, you know what? The atom is actually empty space, and the nucleus is very small, and it's at the center of the atom. Right? He helped us know, because we've never seen the inside of an atom. We've never seen it. We've just used what Ernest Rutherford told us. How did he know? He fired things into an atom. Now, here is what he did again. He fired alpha particles at a nitrogen atom. But this time he was directing these alpha particles towards the nucleus of the nitrogen. So they were going right at the center, hitting the nucleus. Then what he found out is that this nitrogen nucleus, when hit with enough energy by these alpha particles, changed into an oxygen nucleus. Okay? And when it did that, it threw away a proton in the process. It shot out a proton. It ejected a proton. So this is an example of a transmutation reaction. And when we write it, we say we have this 14,7 nitrogen, and it met the alpha particle 4,2 helium. And what it did is it became an oxygen, a type of an oxygen. How do we know? Because the atomic number became 8. And then what it did in the process is it then shot out, okay? It then shot out, sorry, this is actually, it's 4,2, and here would make it 17. Then here we would then put a proton, 11H. Proton was shot out. And this is how it helped us discover this proton. It was shot out and we were able to discover it, right? Now, when we have these type of bombardment, we can say many, many things, okay? Many, many things. But one thing we've seen is these reactions, these bombardment reactions, like this example of transmutation, it helps us to be able to make an element change into another. We are the ones doing it. We are not waiting for radioactive decay. We can shoot a certain particle to hit the nucleus of an element, and that nucleus will change to be a different element. So it is us. We are transforming an element into another in the lab. Okay? Then when it changes to a different nucleus, it can shoot out anything. It can shoot out a neutron. It can shoot out a proton. It can shoot out a positron. It can shoot out different elements, right? Now, but we would have changed it in the lab. Beautiful, beautiful thing. So it is not spontaneous anymore. Spontaneous means we cannot do anything to make it happen or to stop. Our hand is not included, but now we have our hand included. And this is an example. Now, when we look at these nuclear bombardment reactions, sometimes, and an important thing about them is sometimes you may be given in abbreviation notation or in an abbreviated notation, or you may be asked to convert to an abbreviated notation. So they may give you in an abbreviated notation and ask for the reaction, for the nuclear equation itself, right? They may ask for the nuclear equation when they give you the abbreviated notation. Or they can give you the nuclear equation and ask for the abbreviated notation. So what is this abbreviated notation? How do they write it? Now, when we have this, we have important particles. And when we have these important particles, here's the one. This is called the target. This is the target element, the element we are shooting at. This is the target nucleus, okay? Let's not say target element, but because we are focusing on the nucleus. This is the target nucleus, right? Target nucleus. Then here we would have our incoming particle, and then which is the particle that is firing. It could be an alpha particle, it could be a beta particle. Then after this, we have the ejected particle, the particle that, or let's say the ejected, let's say we have the product nucleus. We have the product nucleus because it's a nucleus first, and then we have our ejected particle. So what we do is when we are writing, this is the ejected particle. Ejected particle. When we are writing in abbreviated notation, we care about the target, incoming, product, ejected. We don't have to remember the names. But our target, the original element, we just write it as it is. So when we are writing in abbreviated notation, so here is the abbreviated notation. Let's put it. Abbreviated notation. Abbreviated notation. When we are writing in abbreviated notation, this is how we put it. We'll put our target nucleus 14,7 nitrogen. Then what we do is this guy and this guy, the incoming particle and the ejected particle are written in symbols. Incoming particle, what is it? It's an alpha. So we put parentheses. And first we put the incoming, then we put the ejected. So alpha first, then you say comma. Then what was ejected was a proton. So you can go and look at the nuclear particles if you've forgotten them. Here, the proton. Then after that, we then just write the product guy, the product nucleus, which is going to be 1780. We write it in nuclide notation, of course. We are done, and this is how it happens. Do you see how easy it is? So let's do questions. Here's the first one. Write the abbreviated notation for the reaction. So here is a reaction, and we should write the abbreviated notation. So we can go ahead. What do? We first write 4020 calcium, then we open our parentheses, right? We open our parentheses. What is this? Now, many of you are saying, you gave us 7, you taught us 7 nuclear particles, but we've never seen where we use deuteron yet. We've never seen any position where we use our deuteron. Here is an example. There it is, this 2,1. Remember, it's a special type of a hydrogen. This is a hydrogen nucleus from the deuterium. Deuterium. When we talk about hydrogen in the air, in its original form, we can have, there are 3 types, right? We said, what is the first one? Protium. Right? This is the first one, which is 99.98%, something like that. And then we have this deuterium, which is 0.02%, I guess. Then we have the last one, which is tritium. Okay, tritium. This is found in, we cannot even give it a percentage. We say in trace amounts, very, you don't really find it in its original form, but it is made during other reactions. So either way, these are the hydrogens, and this guy is the 1,1, which is like this. Then this guy is 2,1, and then this guy is 3,1, like this. Now, when we talk about these hydrogen guys, we just sometimes focus at their nuclei. Okay, the nucleus of protium is a proton. Okay, it is still 1,1, but it is now positively charged, because remember, we are now dealing with it as a nuclear particle. So this bottom number is not only the atomic number, but it is also the charge. So we know that it is a charge of +1. We are talking about only the nucleus of this guy. Then we can take the nucleus of deuterium, we will call it a deuteron. Now this is also 2,1H, but remember it is positively charged. And we look at the bottom number, it's the charge, it has a charge of 1. And these are the important ones. These are the ones we want to talk about. So here we have our it comes from deuterium. It is our deuteron. Deuteron. This guy, how do we put him? How do we put him? We did our examples we put our symbols. We can either write it as 21H or we can write it as just a D, right? We can write it as 21H or we could write it as just a D. So in this case, we usually put it as a D. So I'll put it in like this, as a D, then comma. What is the product? The product here is a proton, right? This is a deuteron because we are only dealing with the particles, not the protium. No, not as a hydrogen. No, we are dealing with only the nucleus. So the nucleus of that guy, which is a proton. So it's just a proton, which we put as a P. Then what is it going to make? It is going to make, so let's put it in orange here. What is it going to make? It is then going to make 41. Oh, we don't put it like this. We then just show 4120. I almost made a mistake. And here you are done. You are done. This is the abbreviated notation. This is your solution for this. Okay, deuteron to protium, blah, blah, and you're done. Now here they say, write the nuclear equation for the bombardment reaction. Now we have it. 12,6 deuterium, proton, blah, blah. So we can just write it. So say 12,6, okay, we add deuteron, which is 2,1 hydrogen, and it is going to form, we can start by putting our 13,6 carbon, then we add our proton, which is 1,1 hydrogen. This is very simple, isn't it? So we know that these were the reactant side, these are the products. All right? And you're done. That's how you do it. And this is it about transmutation. Now we look at nuclear fission and fusion in